Hi guys. So today we're going to start talking about two of the most important functions in all of mathematics and science, and two of the main examples that we'll be using through the rest of calculus. And those are the natural logarithm and the natural exponential function. So you've probably seen those functions in your classes leading up to this class. What we're going to do here is we're going to make those functions rigorous. That is, I'm going to tell you what a definition of those functions is, and then we're going to derive the properties of the functions from the definition. So we're going to be using the alternative approach that is taken in the book. So we're not working from section 6.2, we're working from section 6.2 star, which is after 6.2, 6.3, and 6.4. And the pages are blue. There'll be a page number listed on the module page for this lesson, and that's where you should start reading. So to reiterate, we're going to be looking at 6.2 star, 6.3 star, and 6.4 star. What is the natural logarithm? Maybe you've seen it defined as the inverse of the exponential function. Maybe you've seen it just given to you. There's this thing called ln of x that you can punch in a calculator and numbers come out. So what we're going to do is we're going to try to clarify exactly what it is. And we're starting with the natural logarithm instead of the exponential because if we start with the natural log, it's very easy to derive the rest of the properties that the natural log and the exponential function both have. The natural logarithm is the function defined by ln of x is equal to the integral from 1 to x of 1 over t dt. Now that might look kind of weird that we're defining a function in terms of this integral. So the first thing I want to argue is that the 1 over t, or 1 over x, that function is actually very important in mathematical modeling because it's the sort of function that gives you nice decay to the x-axis as you go to infinity. And when you write this definition down, what you're really doing is you're saying, well, I'd like to define a function so that if I have the graph of the function 1 over t, that I'm calculating the area underneath that function from 1 up to a point x. And so the area underneath here, that's what we define to be the natural log of x. So another thing that might jump out at you is this actually explains why the natural log is negative for values that are less than 1. Because suppose that you wanted to do something like the natural log of 1/2, well, that would correspond to an integral that starts at 1 and ends at 1/2. And one of the things that you should remember is that you can switch the order of the limits of integration by putting a negative sign in front. So this is actually an integral that's going backwards. It starts at 1 and goes to the left. And so it's computing the area in the reverse order that integration is defined, and that's why this natural log is a negative number. Okay. It should also make sense why there's no such thing as the natural log of 0, because there's an asymptote right here. So if I want to integrate from 0 to 1, I can't even use 0 because I have this function that's asymptotically expanding as I go up. We'll talk about what's called improper integration later. And even if you look at it in the terms of limits, that still doesn't make any sense. There's infinite area in here. So it doesn't make any sense to integrate from 0 to 1 for the function 1 over x. So is there anything obvious that we can say about the natural log right away just from the definition? So if the natural log of x is equal to the integral from 1 to x of 1 over t dt, that the natural log of 1 is the integral from 1 to 1 of 1 over t dt. And that's like taking the area of a rectangle that has no width, right? So one of the properties of integration is that the integral from a number to itself of f of x dx is equal to 0. And so the natural log of 1 is 0. The fundamental theorem of calculus part 1 says that if you have a function f that is continuous, and you define a new function, capital F of x, to be equal to the integral from a to x of f of t dt. So this is a function that is basically computing the area underneath f from a to x. So this is an area function, right? So capital F is computing areas. What the fundamental theorem of calculus part 1 says is that if you take the derivative of capital F, it just destroys the integral. d by dx of capital F of x, which is equal to d by dx of the integral from a to x of f of t dt is equal to f of x. So the upshot of the fundamental theorem of calculus part 1 is that the derivative of an integral is the original function, that derivatives and integrals destroy each other. So we're going to use this idea to sort of investigate some of the properties of the natural log. So the natural log of x is equal to the integral from 1 to x of 1 over t dt. What is the derivative of the natural log? D by dx of the natural log of x is equal to d by dx of the integral from 1 to x of 1 over t dt. But then by the fundamental theorem of calculus part 1, this is just equal to 1 over x. So when we introduce a function into calculus, we want to make sure that we understand its calculus properties. Even if you've seen this in a class before, it's not necessarily justified why the derivative of the natural log is 1 over x. In fact, in some scenarios, you just define it that way. It's given to you as a rule. But it turns out to be the case that defining the natural log this way gives you an explicit way of writing down that its derivative is 1 over x. And that means that its antiderivative is also, the antiderivative of 1 over x is going to be the natural log, which is going to fill the hole in the power rule. So now that we've got a definition for the natural log and we know its derivative, we can actually start computing some of its properties. So here's what we know so far. We know ln of x is equal to 1, the integral from 1 to x of 1 over t dt. And we know that the derivative of the natural log of x is equal to 1 over x. So let's see if we can derive some of the natural log properties that you would have seen in the past probably, but we're going to show how you can use the definition that we've made here to prove that those properties are true, instead of just giving them to you as rules that you need to learn. So there's 3 rules of logs. The natural log of a times b is equal to the natural log of a plus the natural log of b. The natural log of a divided by b is equal to the natural log of a minus the natural log of b. And the natural log of a to the r is equal to r natural log of a if r is rational. Okay, that just means that this represents some sort of square root type expression. So I'm going to use the fact that we have these rules up here to prove a couple of these properties, and then one of them will be left for an exercise. So here's property 1. Let's show that the natural log of AB is equal to the natural log of A plus the natural log of B. So the way this goes is you start with derivative. So let's let a be a positive number so that this even makes sense. And we're going to look at the natural log of ax. Okay, so x we can think of as a variable, a is the constant in front of it. So what we're going to do is that this splits up. And we're going to do it by using the derivative. So a is a constant and x is a variable. D by dx of the natural log of ax by the chain rule is going to be 1 over ax times the derivative of the inside, which is a. The a's cancel and we get 1 over x. But d by dx of ln of x is also 1 over x. So ln of ax and ln of x have the same derivative, which means that they must differ by only a constant. If you integrate 1 over x, you're going to get some function plus c. Both of these are that function, but the plus c is the only thing that's going to separate them. If the integral, what I'm saying here is if the integral of 1 over x dx is equal to, if one possible answer to this is the natural log of ax, and another possible answer to this is the natural log of x, then these must differ by some constant c. So the natural log of ax was equal to the natural log of x plus some constant. I plug in x is equal to 1. I get the natural log of a is equal to the natural log of 1 plus some constant. The natural log of 1 is 0. And that means that in this expression up here, what that really said was that the natural log of ax is equal to the natural log of x plus the natural log of a. And that's exactly the rule that we were trying to show. That's actually probably the first proof of the some property of the natural logarithm that you can write down that's rigorous. So as an exercise, and you should try to do this on your own, you should see if you can figure out why the natural log of x divided by y is equal to the natural log of x minus the natural log of y. It's the same sort of argument that we just did. I could write a proof out, but one of the more amusing things to do here, without cheating and looking at the book, is to try to see if you can use the ideas that I've already done in the previous argument to show that this argument must be true. And then I'd be very interested to look at your proofs if anybody comes up with one. What do we know about natural log now? We know that the natural log of 1 is 0. We know that the natural log of x, if I run off to infinity, I get infinity. The reason is because I keep adding area. I know that if I run off to 0 and I stick strictly to the right of the asymptote, I get minus infinity. Now, why is that? Remember that we're looking at areas under this curve right here. So if I keep adding area this way, then the area here goes to positive infinity. And if I start at 1 and I add areas in the other direction, so I head this way towards the axis, then the areas I add up in here head to minus infinity. And they're negative infinity because we're integrating to the left. To complete our study of the properties of the natural log, we're going to look at this problem. Find d by dx of the natural log of the absolute value of x. Understanding this problem will help us complete our study of the properties, and then we can move on to exponentials and also computations. So the first thing I have to do when I've got absolute values in a problem is to split the problem up into its two branches, because I don't know how to take a derivative of an absolute value. So there's actually two different problems encoded in the same problem here. So the natural log of the absolute value of x is equal to the natural log of x when x is positive, and it's equal to the natural log of minus x when x is negative. And of course, it makes no sense when x is equal to 0. So let's actually do two derivatives separately. D by dx of the natural log of x, well, that's 1 over x, and that holds when x is positive. And d by dx of the natural log of minus x, well, that's 1 over minus x times negative 1 by the chain rule, which is also 1 over x. Well, what that means is, if the derivative of the natural log of the absolute value of x is equal to 1 over x, because on both branches it's the same thing, then the integral of 1 over x dx is equal to the natural log of the absolute value of x plus c. So if you've in the past wondered why the absolute values are in the definition of the integral of 1 over x, if you've seen that before, this is why. That the derivative on the right side of the real line and the derivative on the left side of the real line are the same thing. So when you undo 1 over x with an integral, you have to put the absolute values in until you know which part of the domain you happen to be on. Okay, so what that means is that we're in a position to fix the power rule now. So remember that the power rule says that the integral of x to the n dx is equal to x to the n plus 1 over n plus 1 plus c if n is not equal to negative 1. And so what the natural log does is it fills the hole. And if n is equal to minus 1, then the integral of x to the minus 1 dx is the integral of 1 over x dx, which is equal to the natural log of the absolute value of x. Okay, so that finishes our ability to take integrals of polynomial-like objects. So what are some cute things that we can do with a natural log? Well, the first thing is we can use the natural log of x in u substitutions. Okay, and that means that we're going to be able to write down antiderivatives for trig functions that we didn't have access to before. So in particular, we can say things about, say, the integral of the tangent. So the integral of the tangent of x dx is equal to the integral of the sine of x over the cosine of x dx. And this is a u substitution, because I can take the cosine of x here and I can turn that into a u. If u is equal to the cosine of x, then du is equal to minus the sine of x dx, which means that minus du is equal to the sine of x dx. And this integral turns into the integral of minus 1 over u du. And since we know what this is now, we can write it as a natural log. Minus 1 times the natural log of the absolute value of u plus c, and that's equal to minus 1 times the natural log of the cosine of x plus c. So this is where the antiderivative of the tangent comes from. So you need to know the natural log and its structure in order to derive this. Okay, you can do the same thing for the cotangent, which I encourage you to try. The last idea that I want to introduce is called logarithmic differentiation. So logarithmic differentiation is a way of attacking complicated derivatives where you'd have to use crazy product and quotient rules. Because remember, what a logarithm does is it takes products and it turns them into sums, and it takes quotients and it turns them into differences. So the log of a product is equal to a sum, and the log of a quotient is equal to a difference. And so that means if I'm taking derivatives, if I can somehow get logarithms involved, I can take things that would require me to use product and quotient rules and turn them into addition problems instead. So let's consider this function. Y is equal to x plus 1, x minus 1 over x squared plus 1. And suppose I want to find y prime. So if I just do it normally, this thing is going to be a quotient rule with a product rule inside of it. And that's going to be a long computation. So there's sort of a more computationally efficient way to attack this, as long as we're willing to deal with implicit differentiation. So the strategy is going to be that we're going to apply a natural log to both sides. That's legal because a natural log is a one-to-one function, and so I haven't destroyed any information by doing that. The natural log of y is equal to the natural log of x plus 1, x minus 1 over x squared plus 1. So I've shifted the equation from being an equation in y to being an equation with natural logs involved. So why would I do that? Because the natural log is going to let me break this up into a pile of sums and differences. So we can expand the right-hand side. So remember that the natural log of AB is equal to the natural log of A plus the natural log of B, and the natural log of A divided by B is equal to the natural log of A minus the natural log of B. So if I do that to the right side here, what I get is the natural log of x plus 1 plus the natural log of x minus 1 minus the natural log of x squared plus 1. So I've taken this is a product, and so it turned into a sum. This is a quotient, and so it turned into a difference. Now remember, ultimately the goal here is to take a derivative, and it doesn't look like I've made anything easier at this point. But look what happens when I take a derivative with respect to x of both sides. So if I apply a d by dx here, and I apply a d by dx here, the left-hand side I have to do with implicit differentiation. Because remember, y is not a variable, it's a function. So what you get is this. The derivative of the natural log of y is 1 over y times the derivative of y. And on the right-hand side, I have some very easy derivatives. The derivative of the log of x plus 1 is 1 over x plus 1. The derivative of the log of x minus 1 is 1 over x minus 1. The derivative of the log of x squared plus 1 is equal to 1 over x squared plus 1 times the derivative of the inside by the chain rule, which is 2x. So at this point, I have an expression where I'm almost done. See, I've got this dy dx right here. dy dx is what I wanted to find. This derivative did not involve any quotient rules or product rules. So all I've got left on this side is this y. So if I could pull the y over to the other side and then turn it into a pile of x's, then I would be done. I'd know the derivative. But look, I know what y is equal to. So the last step in this problem is to write that y dy dx is equal to y times 1 over x plus 1 plus 1 over x minus 1 minus 1 over x squared plus 1 times 2x. But I know why. This is equal to x plus 1, x minus 1, x squared plus 1, 1 over x plus 1, 1 over x minus 1, 2x over x squared plus 1. And I don't know about you, but I find this incredibly easier to compute than if I started here and I took a bunch of quotients and chain rules. Notice when you do a bunch of quotients and chain rules and product rules, you still get big complicated algebraic expressions. So you haven't added any more complexity to the way that the answer comes out here. It's just that the computation that you did to get from here to here is more straightforward. Now, if you need a reminder on implicit differentiation, please let me know. This is an incredibly powerful idea, and it's one that I really want people to know going forward. Okay, so the next video will cover examples of logarithmic computations, expansions of logarithms like we did right here, and also an example of another implicit differentiation. Okay, see you.